Philip. The stage is yours.
Thank you very much for this kind introduction. So the title is To Rework or Not to Rework. So it's about how you can use causal machine learning to derive data-driven decisions, how to do the best possible rework decisions. Before we get started, maybe Philip shortly introduce Osram. Probably everyone knows, but so that you have some background what they're doing.
So let me lose some words about Osram. Here on this slide, you can see the key figures of the company. AMS-Osram is a semiconductor manufacturer of optical solutions. The portfolio ranges from sensing solutions over automotive interior and exterior solutions up to horticultural lighting solutions. And the other project partner with which we did this work together is Economic AI. And
maybe some brief words. Everyone knows Osram, but Economic AI probably is not so much well known. It's a spin-off of MIT and University of Hamburg, where the idea was bringing causal AI, causal machine learning into practice. We are mostly doing three things. One is consulting projects, so where we develop data-driven methods for companies, mostly tech companies and platform, because they have many causal problems and a lot of data. Then we also do trainings from very high level for top management to technical trainings for data scientists, because causal machine learning, causal AI, it's a quite new field which big impact on industry. And the last one is software development. So we have developed WML. It's one of the leading open source frameworks for causal machine learning. And we're also working on some commercial versions, and some software we developed is also used in this project. And now we can start with the project. So back to Philip.
So let's start with some motivation. Since it's not long until Christmas, I thought we just do some cookie mass production here. And we just suppose we are very well prepared and set up. We have the best equipment, the best recipes passed down for generations from our grannies. And of course, we have the secret ingredient, and we also are very confident in our skills. So after some manufacturing, a very decent looking production lot emerges. This baking plate here depicted in the middle. And after just one more step, after the baking, we arrive at a not so good result, a very inhomogeneous result. So, and even so, we stick to the recipe very closely, and even so we did our best, we have some cookies that are scrap, they are just burnt. But others turned out very nicely in a golden brown color. And again, others just would need a little longer of baking, just 1 or 2 more minutes. And so the question arises, should we put this baking plate again into the oven and give them 1 or 2 more minutes of baking? And that is the main question of our talk. Upon inspection of a production lot, should we do rework or should we not do it? Because if we do some estimations and from our experience some counting, some cookies might degrade just if they are too long in the oven, while others might benefit. So in the end, we might estimate some yield improvement of 6 out of 20 cookies that are turned out perfect if we do another round of baking, and compared to 5 out of 20 cookies that are perfect right now. So most of the time at AMS-Osram, we are not concerned with the mass production of cookies. We actually manufacture, for example, white light emitting diodes. And on the left, you can see one application of white light emitting diodes. It's this classical automotive headlamp. And how do you do it? You start with a blue light emitting ground substrate. And up on this ground substrate, you dispose some phosphor conversion layer. And this has the effect that the blue light is shifted into the white light region. On the right, you see the manufacturing process. Here it is for quadratic areas are our baking plates. And there are single LEDs up on it. And over these baking plates, there moves a spray gun and applies a very thin layer of phosphor, organic phosphor. So let's jump a little more closely into this conversion process. As I said, we start with a blue light-emitting ground substrate, depicted here by the red dot. And when production finishes, we want to be at the final target point, TF. And so we apply our recipe and apply some conversion layer, and this shifts our color point towards the white region along a so-called conversion curve. This is what physics tells us. And if we follow the recipe until the end, until this conversion process is finished, we are very closely to our converted target point. And now the following manufacturing steps are carried out, like molding lenses on top of the LED and whatnot. And from our experience, we know that if we were very closely to this converted target point before, after the production, we are very closely at our target, at our final target. So all in all, we have two measurement points that are important for us. The first one is the measurement after the conversion process. This allows us to do maybe some adjustment to the process, maybe some rework. And the second one is the final measurement after the product is finished. And this is going to be, of course, our target metric. Again, like in the example with the cookies, we calculate the yield of the LEDs, that is the share of good LEDs, the LEDs that satisfy the specification and are close enough to our target point. So sometimes it happens that despite sticking very closely to the recipe, we fall short on this conversion curve. And our product engineers, process engineers came up with a solution for this. They said, hey, why not apply one additional phosphor coating layer to it? And again, like with the cookies, the question is raised to rework or not to rework. And we can, for this question, we can use the information we have, that is this color point C1 after the end of the regular conversion process. And if doing so, we might land closer to our converted target, and then hopefully later on, if production is finished, closer to our final target. Yeah. At the moment, at the moment when we recorded the data, this decision was carried out through experience from the operator. The operator observed this mean color point, and then he decided upon the distance to the converted target, hey, should I do the rework or should I rather not do it? And important here is we cannot go back once we overshoot on the target. Once all the cookies are brown, we cannot rescue them anymore. And another important thing to note here is that we treat every item in the lot equally, though it's not cost efficient to single out individual LEDs and try to repair them. So much for the introduction of the application and the motivation. With this, I hand over to Martin.
Thank you very much, Philip. So this was a problem setting. Now, what was the idea? Philip also laid it out. So we have this problem to make decisions when to rework or not to rework. Currently, it has been done on more gut feeling, rules of thumb of the operator, but the idea was developing data-driven rules, and in the ideal case, really lot specific, so that you have, in some sense, individualized treatment rules to improve the process. And the ultimate goal is, of course, increasing the yield and avoiding waste, which is expensive. And to do this, we have a causal problem, and therefore we use double debiased machine learning, which is one new method which was developed by my colleague Viktor Chernosukov. We have been working on this, which is a way which allows us to use machine learning not only to make predictions, but really to figure out causal estimates. So here, very high level, on the top you see the manufacturing stages. You have different kind of stages in a linear process, and at each step there are certain characteristics, denoted X, which describes this state. Now in rework, we put one step, single out one step, SK for example, and now we build in an inspection stage where we take some measures, and then we take a decision. And depending on the outcome, we either move forward, or we do a rework step, or in the extreme case, it's waste and cannot be rescued. And now here, this is the key causal diagram. So here we have a certain, in causal machine learning, you call it intervention A. It's the rework decision. Either you have a lot, and now you take, which is not perfect, now you need to take one decision. Either you rework or do not rework. So this is our treatment variable. And Y is the outcome, is the yield of the lot. And now we would like to know what is the effect of rework on outcome. So this is our causal problem. And of course, there are certain confounders, like X, P, and X. These are variables we need to control for, which describe the production stage. There might be, for example, during the production, high workload in the lab, so that this has an effect on the rework decision, but there might also be some variables describing the lot itself, because at the lot they're taking some measurements on the, at some points at the lot, and this information is available, and we would like to use this information to make data-driven decisions when to rework and not to rework. But we need to account for all these variables. If we would not do this, we would get invalid results. We have data, approximately 70,000 production lots from the past. We know background information, what was the workload. We know information about measurements of the chips. We know which action has been taken by the operator and what was the yield. And this is the data we use, and now we use double machine learning to infer from this data what is the effect of rework and how to improve this. And here you see again the actual output, so Cx and Cy are two important measures, and in the past the operator decided, and this was mostly driven by gut feeling of this value. So you can see the orange points have been not reworked, the blue ones true have been reworked, and this was more, as I said, you have this in many problems in many industries where people make decisions on a gut feeling, but not really data-driven. And the idea here is now to make it more data-driven. Here, I skipped this more technical part, so some conditions to apply double machine learning are valid. And now we want to use this to estimate different kind of effects. So the first one we estimate is the so-called average treatment effect. So this is, if you have an intervention, what is the effect of this intervention on average on the whole population? The second one is the average treatment effect of the treated. This effect tells us for those lots which have been actually treated, what is the effect for them? This is a more interesting quantity because we're not interested what is the effect of rework for lots which are so good, which are never reworked, but we would like to know what is the effect of this subgroup for which the policy is targeted. And then to derive lot-specific policies, so we do not want to have one policy for all, so that we do a more refined policy. So this is some kind of, you know this from personalized medicine, targeted marketing, where we really would like to, in a data-driven way, specific policies. And for this, we need the conditional average treatment effect, which tells us how does the effect of the rework depend on certain characteristics we measure. If we know the case, we can then derive optimized data-driven policies. And here, this is the technical part. The double machine learning has really good theoretical properties. So it gives us unbiased estimates, which standard machine learning AI would not give us. Here are some technical slides which are needed to get double machine learning work. If you have questions, we can dive into this in the, it's not called meet and greet, in the panel discussion in the afternoon. And if you're more interested in this, you can also go to the WML page where there are some documentation and some reading to get started. But here now, we can see the actual results of applying different kind of methods. So in the first row, we use a standard estimator of this average treatment effect of rework. And surprisingly, here we get the negative effect. And this would tell us, don't rework. Of course, this does not make sense, but standard methods here fail because they're correlation-based and cannot really back out the true causal effect. If we now use double machine learning, one method of causal machine learning to estimate the overall effect from our data, we see now it gets positive, which of course makes more sense. So the overall effect of rework is positive. And the average treatment effect of the treated is even larger. So for those bad lots which get the treatment, we get an even much larger effect of improving the yield by 4%. So this is the first estimate, is rework beneficial? And now the second part, the probably most interesting and most relevant part is, can we come to better decision by taking into account more information and deriving, it's called policies, so really lot-specific policies. So for a lot, we decide for each lot what might be the best thing to do for this specific lot. And lot-specific means that it depends on characteristic how we can measure. And here, now we estimate for several variables the so-called CATE, the conditional average treatment effect. I mentioned this before. Usually, the first step is calculating what is the effect on average on the population, but a treatment, the effect of a treatment might vary with different kind of variables. If you think about medicine, the effect of a medicine is different for men and women. It depends on the age and other characteristics. This is called CATE. And now here, we use double machine learning to derive how does the treatment effect vary according to certain variables. So the first 2 or 3 are the measurements of the light frequency, which is probably the most important factor. But here we also see that the effect of this variable on our yield is not constant. It's really depending on the concrete value. And if we know this, we can optimize, because we know for which values we should rework and for which values we should not do rework. So we get now a much finer, more granular policies. And the last image is, how does the effect of rework depend on the workload, which also has an effect which is not constant. But now with these methods, we really can figure out how does the effect change and then derive the optimal policy. Here again, the main color point measure. So this is one measurement which is taken on the lot. And here again, we see clearly a nonlinear effect of the dependence of the yield on this measurement. And now we can exploit this to derive the optimal policy. But of course, the optimal treatment might not depend only on one variable. It can depend on several variables. Here's some technical background I skip. But then we use trees. Maybe some of you know trees, which are popular machine learning methods to predict. But here we use so-called policy trees, which allows us to give data-driven decision rules when to rework and not to rework. And now this is the final outcome of the project, that we now have some kind of data-dependent rule when to do rework and when not to do. So here you see some variables like CM, invalid, the variance of CM. So these are all variables we have are available. And now, depending on these values, this trees gives us what is the optimal decision. So now if you have a certain lot with certain characteristics, you can go down the policy tree, and then it tells us A equal to 1, rework or do not rework. And now we really have a data-driven, refined, optimal policy rule when to do rework, not to rework. And now the next question, of course, is what do we benefit from this method? So how much do we gain? And here we see the comparison of the different kind of methods, what decisions they would propose on our given data. So here on the left, you see what we from the past data, what has actually been done. And then we see this different kind of methods. So conditional average treatment effect based only on one variable, on the most important main measurements, if we do this on 2 variables, or if we do policy trees. And you can see, if you have a clear look at this, that they come for different kind of objects, often also to different kind of decisions. And now we can also quantify what is the benefit from using these data-driven methods. And of course, rework costs something, but it also gives you a benefit because it increases the yield. And for the optimal decision, you need now to take into consideration what are the costs, what are the benefits. The costs usually are very secret, therefore it's some hypothetical calculations. If the cost would be 0%, 1%, 3%, what would be the gain? And here we compare this to the actual policy, and we see, because time is running out, only the final result. So average the yield increases by 1 to 3 percentage point, which sounds not much, but it's really a huge amount if you think about how expensive chips in the semiconductor industry, how expensive the slots are. So this is really enormous saving. So this was, as time is running out, everything in a nutshell. So, but here we derive data-driven policies for optimal rework decisions. And if you have any questions, we have in the afternoon the panel session. We are looking forward to questions, comments. So thank you very much for your attention.
Thank you.